This lesson covers basic concepts of probability and is not extremely heavy on the math, but more definitions and concepts with a little bit of math in there. So as we get going, first of all, some definitions. In probability, when we're talking about an event, this is just talking about the outcome of procedure. So if you flip a coin, whatever happens, that was an event. So it's definitely not your social calendar event. A simple event is an outcome or event that you cannot break down any further into simpler components, okay? And we will talk about that a little bit more, but like a simple event might be flipping a coin, whatever that outcome is, that's as good as it gets. But on the other hand, if you were to draw a card, drawing a card is not exactly a simple event because we could draw a queen, or we could draw a red, or we could draw a red queen. And drawing a red queen is not a simple event. Drawing a red is. We can't break that down further. You know, it's just kind of one of those things. And that'll make a little bit more sense as we go. Now, sample space is a list of all the possible outcomes, every possible outcome. And so when you list that, you then have a sample space. So let's just look at those definitions in consideration of what if we are rolling a die. If you roll a 6, it's an event. Rolling an even number, that's an event. Rolling a 6 is a simple event. You cannot explain that anything out. But rolling an even number is not a simple event because we could break that down further. We could say we rolled a 2, a 4, or a 6. So rolling a 6 is an event, so is rolling an even. Rolling 6 is simple, rolling an even is not because we can break it down further. The sample space is that list of all possible outcomes, so when you roll a die, your only possible outcomes are to get a 1, 2, 3, 4, 5, and a 6. So that's your sample space. When we talk about probability, notation is a big thing. It is in lots and lots of mathematics. Probability, then we're going to say P. And when we see that capital P, we're just going to say that's the probability of something. And then we use letters within that, and there can be other letters, or sometimes we use words that denote specific events. And so if we say P and then parentheses with an A, we read that the probability of A. Even though there's not all those words there, it's the probability of A. Now, probability is always a number that is between 0 and 1. And that is such simple information, but it's going to be very important to you because on some of your homework, they're going to give you a list of numbers and say which ones of the numbers cannot be possibilities. And so you need to just make sure that you choose things between 0 and 1, inclusive, which means it's okay if it's 0, it's okay if it's 1. But they're going to throw some numbers at you that are a little bit strange looking. So just consider if they gave you a list of numbers, can the square root of 2 be a probability? Well, you might not be familiar with what the square root of 2 is right off, so you want to pick up a calculator and punch it in. The square root of 2 is approximately 1.4. So that's too big. It's not possible. Okay, it's not possible for that to be a probability. Now, probability is expressed in several different ways. In a lot of literature, they are expressed as percentages. So, and you might hear me say something like 50% chance. And we use that a lot of times, you know, when they give the weather, they'll tell us, oh, there's a 30% chance of rain. And that is a probability. However, they're generally not going to be used in this course. So if it tells you that there's a 30% chance of rain, you're not going to enter that 30% for your answer, okay? You're going to have to change that percentage to a decimal, 0.30 or 0.3. They may take it as a fraction, but expect them to want the answer in a decimal form. And if you need to round it, they'll tell you what to round it to. But typically, we round those to 2 to 3 places after the decimal. Okay, so even though you can give probability as a percentage, don't expect to do that in your homework. Now, there are 3 different ways to find probability. That's kind of surprising to some people, but it'll make sense when you think about it. Relative frequency. Relative frequency is based on how many times something's actually happened. It is generally an approximation because it's not always going to be the same if somebody tries to repeat that. So you can consider, well, I can take a survey and then find out how many times somebody said something and then how many times we asked people, and then we can calculate the probability that somebody's going to do this. But it's not necessarily going to be the same. If you flip a coin, the probability of getting a heads is 1/2 or 0.5. But if you actually flip a coin 10 times, that does not mean you will really get it. You will not get heads necessarily 5 times. If you calculated your probability based on your experience then, or observations of someone, that's relative frequency. Classical probability, though, is based on equally likely outcomes. And equally likely outcomes is the number of ways A occurs in your sample space out of the number of different simple events possible in your sample space. So this is where we say if you have a fair die, rolling any one of the numbers that's on the die is equally likely. So when you make that sample space, 1, 2, 3, 4, 5, 6, there are 6 different events in that sample space. However, there are, if you said, well, what is the probability then of rolling a 6? There's only one way that happens. So that makes your probability for rolling a 6, 1 out of 6. But if you said, well, what's the probability for rolling an even? There are 3 numbers in your sample space that are even. And again, there are 6 different numbers in the sample space. So it would be 3 out of 6 or 1/2. Now, subjective is based on knowledge of a relative circumstances. We don't use that a lot in statistics class. It would be rare. We're not going to say never. But you are quite familiar with it. One thing that comes up, I've already mentioned, is the weather. That's why we like to say the weather people are wrong. But just because something doesn't happen doesn't mean there was a chance that it could. Again, when you flip a coin, you may get heads, but that doesn't mean there was no chance that there was tails. So when they tell us there's a 60% chance of rain, we often just think that means it's going to rain. But then it doesn't, okay? They're basing that on their knowledge of relative circumstances, what's going on in the atmosphere and what they know it takes for it to make rain. So that's subjective. When you listen to a sports cast, sometimes you're hearing subjective, sometimes you're hearing relative frequency stats. They'll tell you maybe someone's batting average. Well, that's the number of times they've actually hit the ball out of the number of times they tried to hit the ball. So that is their batting average. On the other hand, they may use some subjective information. When you ask a sports person, you know, what do you think the chances are of this particular team winning the game? Well, they probably have some knowledge on who's playing, who's out injured, what the team is like that they're against, what their stats are, but yet they are not, when they give you a probability of a team winning a game, they're also using some knowledge that is just based on relative circumstances, okay? So the one that we're most interested in class is relative frequency and classical. Relative frequency comes a lot from our statistical surveys and research, and classical then is based on equally likely outcomes. When you are working your homework, this is a word of caution to you. Read carefully. It's a real tendency to just get those numbers and think, hey, I've got to divide because it's the number of possibilities divided by the number. So some students will just tend to take the small number and divide it by the big one and think they're done. But sometimes they're not actually giving you the total. You have to find that total to get the numbers that you need to use in, and it says here previous equations, but it certainly shouldn't say that, just in any of the equations, okay? You have to get the numbers that you're going to need to use in equations. And you might even think right now, well, what are the equations? I haven't had equations. Well, as simple as they are, these are considered equations. So to get the number of ways of outcomes or the number of times the procedure was repeated, you may have to add a couple of different numbers that they give you. Okay, so just kind of slow down. it is very important to read. So here's an example where there is if there is a polygraph or a lie detector test, there's a complexity there because it's possible that the subject did not lie or that they did lie. But in either of those cases, the test may say that they lied or did not lie. So you might need to create a chart. And I have a little note down here at the bottom. Be prepared to make some charts when you're reading through some stuff, at least on scratch paper. You might remember Punnett squares from a biology class where you can say, oh, this is the strong trait and this is the dominant trait and this one's the recessive. So the chances are we may look at some stuff like that. And I may bring up a problem to show you that. Find the probability of a false result. Well, even though it's not listed, typically on these charts, what you want to do is find out, first of all, do you need to add these numbers? I need to take, for the probability of false results, that means I need to get the number of false results over the total number of results. Now, I don't see any total column on this chart. So one thing I want to do is maybe add the subjects actually lied. How many subjects did not lie? I can add that together, and that's going to be 22. 22 subjects did not lie, but 56 did lie. So the ones that didn't lie plus the ones that did lie is my total number of subjects. So that's going to be 78. 78 times. Now I could have also done that going across if I wanted to add going across. Watch this. 44 plus 8 is 52. 12 plus 14 is 26. And 52 plus 26 is also 78. So it actually equals the same thing both directions, and that's the way it should work if you're looking at how many results you had. So I now know that out of my 78 results, that's my denominator. My numerator, how many of these results were false? Well, not all of these numbers represent false. False would be if the subject did not lie, but the test said that they did lie. So these are false. Okay, they did not lie, but the test indicated a lie. And then if they did lie and the test said they did not, those are also false. So I have 8 in one thing and 12 in another, so I need to add those, and I find that that is 20 results that are false. So my probability is 20 out of 78, which does reduce, but most of the time we're going to enter our answers as decimals. So 20 divided by 78 is really what you're going to want to do. So if I take 20 divided by 78, I get this decimal, and of course I'm going to need to round this to whatever they say on the homework, and that's not here on my slide here. So it looks like it's about 0.256. And that would be what they asked you to round it to. So about 0.256. Or in other words, and the reason I took it 3 decimal places is for people in other situations that do use percentages, that would be about 25.6% of the time, but they're not going to ask you to enter that as a percentage over here. So about the Punnett squares, let's talk about that for just a minute. I'm going to bring over a sample homework question for you to look at, and we're not necessarily going to work this one all the way down, but this is a homework. Then you may have some different things in here, but it's talking about parents and their genotypes, brown or red, which consists of the pair of alleles that determine hair color, and each parent contributes 1 to the child. There's brown and there's red. So let's just kind of keep that in mind. We can have brown and red from the mom, and then for the dad we could have brown or red. And then we fill in those Punnett squares, brown, 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 red, red, brown, red, red. It says if the child has at least one brown, that color will dominate. So list all the possible outcomes, and are they equally likely? First of all, if they have one brown, oh, I didn't pick up it doesn't matter. At least one brown, the child's going to have brown hair. What are the possible outcomes? We see then that there are going to be 3 brown hair and 1 with red hair. 3 with brown, 1 with red. Now we're going to make this bigger again so that you can look at it. But really what we're doing down here is our Punnett square. We had this option. We had a brown, 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 red, red, brown, and red, red. Okay, so we had 4 outcomes. You just have to read it real carefully. All right, what is the probability that the child will have red, red? Only one of those outcomes was red, red, but we don't want to put 1 here. The probability is that the number of times it happens divided by the total number of outcomes. So that's 1 divided by 4, and that's 0.25. And it comes out exactly. It does say round to 2 decimal places as needed, but we don't need that. The probability the child will have brown hair color. Now remember, they have brown even if they have a brown red. So there were 3 outcomes where the child had brown hair. That's what I colored. So that is 0.75. Okay, and that finishes up that question. I'm just saying it's a little bit easier to see if you actually make a chart to go along with it. Okay, so the complement of event. The complement of an event is denoted by putting a little bar over the top of the event. And so if we have a bar, that means every time where A does not occur. And sometimes that's easy to count, but sometimes it's easier to get this information by just subtraction. For example, if we said, based on the previous one, if we wanted to talk about the probability of brown hair, that would be the same thing as the probability in our previous case of not red. Well, since we've already calculated the probability of red, I could just say 1 minus the 0.25, and that also gives me that 0.75. Now, there's nothing to say I couldn't start over and do the 3 possibilities out of the 4, but I don't have to. I could just get it by subtraction. And sometimes that's a much shorter way to go about it. Just down here, one more little example. The probability of getting a face card, king, queen, jack, when you draw a random card from a shuffled deck, a king, queen, a jack, 4 suites, there's 12 of those cards, and there's 52 cards in a random deck. And by the way, if it asks you questions about cards and you don't really know, you don't play cards, just look up on Google the sample space for a deck of cards, and there are great images. I've had students before who need to look at those pictures so they can kind of count and see what's going on. But 12 divided by 52 comes out to approximately 0.23. So what is the probability of not getting a face card? Well, again, if you don't want to count all of those, since counting the face cards was actually the shorter, I can do 1 minus 0.23, and that comes out to be 0.77, and that would be the probability of not getting a face card. So we have how to calculate probability, and then what the complement of an event is, what sample space is. Now let's look at this significantly high or low results. Okay, significantly high or low results. It's significantly high or low in probability if the chances of it happening were very unlikely. Like if the chances of it happening were actually less than 5%, and that 5% is very arbitrary. They could say we only want to look at 2%, but your homework is going to use 5%. So like if the chances are less than 5%, and that's where you're going to say, wait a minute, that happened a lot more than I think it should. And there's actually something about numbers and way auditors check accounting, the number 0 and how many times it should show up in numbers probability. And if they see it showing up a lot more than that, then that tends to indicate, you know, that somebody cooked the books. And so that's where they look at that particular thing. Okay, so here's an example from the homework. And we're going to look at whether or not this deals with 5%, and it's just another example of how this might apply. So if there are 1,300 births that are randomly selected, and 34 of those births are girls, does that seem significantly high or significantly low, or neither one? Well, if we say that the probability of having a girl is about 0.5, then we would expect then for approximately half of this to be girls. So what are the chances that it would have just been 34 girls? You know, that seems awfully low. Instead of the 650 that we would expect, if there are only 34, that definitely seems significantly low, because we know that this does not happen a lot. Now, we're going to talk a lot more about details of significance later, but again, with all these words on here, it's significantly high whenever the probability of having that many or more is less than 5%. And it is significantly low if the probability of having that many or less is less than 5%. So notice that the less than 5% or less than or equal to 5% stayed the same in both of them. What happens is it's significantly high if you're looking at the probability of having that happen, or the probability of having it happen for low is fewer. So that's what we're looking at, or high or low, and I don't think you have any that are overwhelmingly detailed there. It's more like what I just showed you, but if you run across something, just send me a message. So what else do we need to talk about then? Well, simulations. We tend to like to do exactly what I said before, the 3 probability approaches. Either actually have something and measure it, okay, like an experiment, and that's where we get our relative frequency approach. However, sometimes that's just not a good idea. And also, classical frequency doesn't always apply, because maybe all outcomes are not equally likely. And then if it's a new sort of event particularly, then we might not have any sort of intuitive information about it, so we can't just use that. So assimilation is sometimes used. And assimilation is particularly important if it's a lot less expensive or if it's dangerous. That's why I have the crash dummy on there. When they change the safety features in a car, they can't look on past experience then to say how those things are going to work. But not everything is going to be equally likely. And they don't have anything else to go on. So what they do is they use crash dummies and then simulate the results for people, and that's just a way to go about it. So just keep that in mind. If we can't use the empirical or classical or any of those issues, then that's what we're looking at. Okay, one last thing here, this is just kind of a tidbit, and we will use this more, and it's about the law of large numbers. Whenever you repeat a procedure again and again and again, relative frequency starts to approach actual probability or empirical. Okay, so it approaches the actual. In other words, we know that when you flip a coin, it should be equally likely outcomes. But when you flip a coin 3 times, you're not going to get half of those to be heads and half to be tails, because for one thing, that's an odd number. But you actually might not even get close. You might get heads every time. If you flip a coin 30 times, you might get heads every time, although it'd be unlikely. But the more you flip the coin, the more the number of times you get heads gets closer to half. This is called the law of large numbers, and you're not going to use it a great deal in today's this lesson's homework, but it's an important concept because this is why when we're doing statistics, we so often rely on the empirical or classical probabilities as opposed to relative frequency, because we know that if we do it enough, then the outcomes will approach those of the classical probability. Okay, so that's the law of large numbers. And by the way, that's actually, one of those things about why the casinos are such a bad thing. If they know that the odds of you winning a game, and I'm going to make these numbers really small, but if the odds of you winning a game is 1 in 50, then that's a pretty small thing. But it could be that you play and you win the very first time you play, and then you play again and you win again. But if you play several times, it's going to get down and it's going to come out in their favor because the odds, the probability is in their favor. The probability is that people will lose. And enough people playing enough games means that the casino comes out ahead. Okay? All right, that finishes up today's lesson.